In this lesson, we are going to talk about limits. A limit is the value that a function or a sequence approaches as the input or index approaches some value. For example, let's look at a function like f of x is equal to x, which is a linear function. We say the limit of f of x, which we show with lim of f of x, when x is approaching, let's say, a value, let's say infinity, is equal to, now when x goes to infinity, f of x goes to also infinity, because you can see that when x is 0, f of 0 is 0. When x is 1, f of 1 is 1. When x is 2, f of 2 is 2. And when x goes to a very large number, let's say infinity, f of x is infinity. This is how we show the limit. We say that limit of f of x when x goes to infinity approaches infinity. The topic of limits is very, very important in mathematics, especially in calculus. And using the limits, we can show or define continuity and the derivative and integrals. Now we are going to talk about the notation here, how we show the limit of a function. We use this notation as I showed before. We say limit of f of x when x approaches c, a value c is equal to L. Now this symbol represents when x approaches the value c, and this is the value of the limit, which is the value of the function when x is getting closer and closer to c. When looking at the limit, there are two ways that the limit can be evaluated, either from the left or the right. When we are talking about the limit from the left hand side, we call it left hand limit. When we are talking about the right hand side, we call it right hand limits. To explain what exactly it means, again, consider the function f of x is equal to x. If we want to find the limit of f of x when x goes from left to, let's say, a number like 2, we are going to write limit of x when x gets to 2 from left. So we say 2 minus. And when we say that limit when x goes from the right, we say limit of x goes to 2 plus. Or if you look at the graph of the function, f of x is equal to x. If number 1 is here, number 2 is here, this is the value of the function at 2. This is 2. When we say from the left and the right, it means when we get closer and closer to x equal to 2 here, from left, meaning we go from here. From the right, we are going from here. And both of them, as you can see, they approach to the same value, which is f of 2. Now, to evaluate the left-hand limit, we are going to use values which are a little bit less than the approaching number. For instance, if it was approaching from left to 2, we are going to use a number like 1.9, 1.99, 1.999, and so forth. And when it approaches from the right, we are going to use numbers which are a little bit greater than 2, which is 2.1 or 2.11 or 2.001. very close to 2, but not less than 2. Always greater than 2 if you are approaching from right. If you are approaching from left, we are going to use numbers which are less than 2. Now we are going to define if limit exists. 3 conditions has to exist. First of all, the left-hand side limit has to exist. This is the first condition. The right-hand side limit has to exist, and also left and right-hand side limits, they have to be equal. So, for a function to have a limit at a point, left-hand side limit, right-hand side limit, they have to be equal and they have to exist. This is the main condition for a function to have a limit at a given point. We define a continuous function as a function that is defined at every single point. This is what we call a continuous function. Now, informally, we can define a continuous function if and only if we can draw the function without lifting our pen. For instance, in the given example here, since when we draw the function up to here, we have to lift the pen to draw this part of the function. This graph is discontinuous. In the first example, it's asking us which of the following series has a limit, and if it doesn't have a limit, why it doesn't have a limit, and use a graph to support our answer. For the first one, which is this series, we can see as n increases, the value of the end increases too. You can also see from the terms here, 1, 3, 9, 27, when n goes to infinity, the last term, which is here, this becomes 3 exponent infinity minus 2 when n goes to infinity. Infinity minus 2 is the same as infinity. Any number exponent positive infinity is going to be infinity. So this means that this series is going to go toward infinity as n, or the number of terms, increases. So this means that this series does not have any limit here. And we can plot this one. This one is n, and this is the value of the series. We can see that the first one is 1 over 3, the first term. So the first term is very, very close to the n axis. Then the next one is 1, which is term 2. So if this is 2, this is the value 1, this is term 2, this is term 1. Then term 3 is 3, so it's going to be somewhere around here, and this continues going up. So that shows that this series here is not going to have any limit. The next series is this one. We are going to say the limit of n over n plus 1 as n goes to infinity again is the same as, in the numerator, the contributing term is n. In the denominator, the contributing term is n again, because when n goes to infinity, infinity plus 1 is going to be the same as infinity. So it's going to be n. If we simplify n and n, we get 1. This means that this series is going to have a limit of equal to 1. The reason is that 1 over 2 is going to give us 0.5. 1 over 2 is really 0.5. Then 2 divided by 3 is going to give us 0.6. Repeated 6. 3 over 4 is going to give us 0.75. 4 over 5 is going to give us 0.8. And you can see that these numbers, they are getting closer and closer to 1. So this series is going to give us a limit of 1 when n goes to infinity. We can also plot this one. Term 1 is 0.5. This is 0.5. Term 2 is 0.6666, which is somewhere around here. 0.3 is a little bit higher, 0.75. Term 4 is 0.8, which is somewhere around here. You can see that the graph is going to look something like this one, which represents a limit approaching to 1. The next question is to look at the graph given here and determine limit of x going to the left of 4, to the right of 4, to the 4, the value 4, and the value of the function at 4. We can see that if this is x, if we go from the left of 4, meaning this way, the function is going to be negative, the limit is going to be -2. When we are going from the right, meaning this way, we go like this, and then when we approach 4, the limit is -2 again. Now the limit of the function at x approaching 4 is going to be -2, and the function at 4 is also -2. And this function is continuous because I can draw this graph without lifting my pen, or the function is defined at every possible value of x. The next question says, state the limit of the sequence represented by each graph if it exists. If it doesn't exist, we have to explain why. In the first graph, A, you can see that the limit is going to be here, which is 4. This is the limit for the first one. The second one, you can see that when the n value increases, if the n value is an odd number, 1, 3, 5, 7, and so forth, the limit becomes plus infinity because it goes up. And when it's even number n, 2, 4, 6, and so forth, the limit becomes -infinity. Obviously, there is no limit because the left hand and the right hand side limits do not exist. They are not equal. So no limit here. And the last one, which is graph C, as you can see, when n is increasing, the function is always equal to 3. So the limit is 3 in this case. The next question says, consider a function y equal f of x given the following information. The limit the left hand side limit at 3 is 2, the right hand side limit is 2, and the value of the function at 3 is -1. The part A says function f of x is continuous at x equal to 3. The answer is false. The reason is that the left hand side limit and the right hand side limit, although they are equal, they are not equal to the value of the function at x equal to 3. So this means that the function is not continuous at x equal to 3. The limit of f of x as x approaches 3 does not exist. The answer is false. The reason is that the left and right hand side limits do exist and they are equal. So it means that the limit of f of x as x approaches 3 does exist. The third one, the value of the left hand limit is 2, which is here, which is correct. So this is true. The next one, the value of the right hand limit is -1, which is incorrect because the value is 2. When x is equal to 3, the y value of the function is is 2, which the answer is false because when x is 3, the value of the function is -1. So this is false. The last example says, looking at this graph, which is shown here, state the domain of the function. We can see that the function is defined for all values of x, so we can say domain is equal to x such that x is in R, the real numbers. Next, evaluate the following. Limit of x going to -2, which is here, from left hand side. You can see that when we approach -2 from left, the value of the function is 0. The next one says the value of the the limit of the function when we go toward -2 from right. So we go this way, and again the value of the function is 0. Then it says the limit when x goes to -2. We can see that the left and right limit are equal and equal to 0, so this is 0. And also the value of the function at -2, which is here, which is going to be 0. Now the last part of the question says, is the graph continuous at x equal to -2? You can see that I can draw the graph without lifting my pen at x equal to -2, so this is continuous. Or we can say, since left hand side limit exists, the right hand side limit exists, and also left hand side is equal to right hand side is equal to the function at -2, this function is continuous at x equal to -2.